So this screencast begins our next kind of foray into spectroscopy with infrared spectroscopy. Um, when we talk about infrared spectroscopy and compare it to mass spectrometry can tell us things about the structure and it can tell us things about the molecular weight, but it doesn't give us all the information. So a lot of times when you have to identify a molecule, you don't just use one technique, you use multiple techniques. And so infrared spectroscopy is very good at identifying what functional group is present in a molecule. And so we are going to work right here in the infrared region of the electromagnetic spectrum. And so I want to review that just a little bit. Electromagnetic radiation is radiant energy having dual properties of both waves and particles. Okay. And so a lot of times we abbreviate this as EMR. So you'll see that abbreviation, and it's just radiant energy having dual properties of waves and particles. Okay. Now, particles of electromagnetic radiation are called photons, and each has a discrete amount of energy called a quantum. So a photon is just a particle of electromagnetic radiation and has a discrete amount of energy called a quantum. Right? And so electromagnetic radiation can be characterized by its wavelength and its frequency. And so wavelength is shown with a lambda, and that's just the distance from one point on a wave to the same point on the adjacent wave. Right? And this is a length. So a lot of times it is measured in maybe nanometers or micrometers. And so I just wanted you to remember some of these conversions that you probably used in general chemistry, but it's been a minute, and so it's always good to review. Then it also another kind of important characterization of electromagnetic radiation is frequency. Frequency is shown with the Greek letter nu. It's shown as a cursive V. Your book is a lot of times we'll use a V that looks more like a V, but I want you to be able to recognize both. And it's just the number of waves passing per a unit of time. Now, this is generally reported in 1/seconds, which I want to remind you can also be shown as seconds to the -1, but it's also called hertz as well. So those are the units that we encounter for frequency. Now, the electromagnetic spectrum is arbitrarily divided into different regions, ranging from gamma rays here to radio waves here. The visible light only really occupies a small region of the electromagnetic spectrum. And when we talk about infrared spectroscopy, we're in this region of the infrared spectrum, here in the infrared. Now, I want to review a few things, right? All electromagnetic radiation travels at the speed of light, which is c, which equals 3 times 10 to the 8th meters per second, right? And the energy of a photon is directly proportional to the frequency, right? So, right, as the energy increases, the frequency increases. As the energy decreases, the frequency decreases. And we can relate this through a equation where energy equals H, which is Planck's constant, times the frequency. Since energy and wavelength are inversely proportional, that means as one goes up, the other goes down, right? Energy decreases as the wavelength increases. And just as a reminder, if E equals h nu, that also equals h times the speed of light over lambda, because the frequency equals the speed of light over lambda. Now, all of this you should have talked about in general chemistry, so it's just a brief review. So when we talk about these relationships, it'll be fresh, right? Now, when electromagnetic radiation strikes a molecule, some of the wavelengths are absorbed. Not all of them are, but some of them are. So for absorption to occur, the energy of the photon must match the difference between the two energy states in the molecule. And so this is the ground state and this is the excited state, okay? The larger the energy difference between the two states, the higher the energy of radiation needed for absorption, okay? And so higher energy light, that UV visible, causes electronic excitation, but lower energy radiation, like infrared, causes vibrational excitation. And so we're interested in that vibrational excitation, okay? And so what this means for us is that absorption of IR light causes changes in the vibrational motions of a molecule, right? So when we talk about different vibrational modes available to a molecule, there are two that we're going to talk about. One is stretching, and this is where, if you kind of imagine two atoms that are bonded, and here is their bond, and it's like a spring, and you can stretch it, and then it can also compress, right? So it's stretching back and forth. And then you can also have bending, where we've got a central atom here and these two molecules, and they can bend in towards each other and come back out. And so that's what we see when we talk about IR absorption. Now, the vibrational modes of molecules are quantized. And so what that means is they only occur at specific frequencies. And those specific frequencies correspond to the frequency of IR light. Okay. Now, when the frequency of IR light matches the frequency of that particular vibrational mode, the IR light's absorbed, and it causes the amplitude of the particular bond to stretch or bond bend, right, to increase. Okay, and so we'll see that these will then increase when they absorb light. Okay, so we can summarize that by saying different kinds of bonds vibrate at different frequencies, so they absorb different frequencies of light. Okay, and so IR spectroscopy distinguishes between the different kinds of bonds in a molecule, so you can determine the functional group. So let's look at what an IR spectrum looks like. Okay, so in an IR spectrometer, light is going to pass through a sample, and frequencies that match the vibrational frequencies of the molecule are absorbed, and the remaining light is transmitted to a detector. Now, an IR spectra is just a plot of the amount of transmitted light here on the y-axis versus the wave number here on the x-axis. Now, a few things to point out here. Most bonds in organic molecules absorb in the region of about 4,000 wave numbers to 400 wave numbers. It's divided into two regions. There's the functional group region, which is from about 4,000 to 1,500 wave numbers. And then the fingerprint region is 1,500 to 400 nanometer wave numbers. Sorry, I said nanometers, wave numbers. And just like a fingerprint, this is really specific for the individual molecule. So we are mostly going to look at the functional group region, which tells us what the functional groups are. So I want to point out something about wave numbers. Wave numbers are sometimes shown as a V with a line over it, and that just equals 1 over the wavelength. So just kind of as a heads up there, you're going to see that sometimes. So frequency generally increases as the wave number increases. Okay. Now, where a particular bond in the IR absorbs depends on the strength and the atom mass. So where a bond absorbs in the IR depends on bond strength and atom mass. Stronger bonds so like triple, remember, is stronger than double, which is stronger than single. Okay, so we talked about that earlier, but don't forget, vibrate at a higher frequency. So they absorb at higher wave numbers. Okay, now that means bonds with lighter atoms are going to vibrate at a higher frequency, so they absorb at higher wave numbers too. Now, Hooke's law describes the relationship of frequency to mass and bond length. So Hooke's law describes the relationship of frequency to mass and bond length. Right? And so basically, when we look at this, we have a stronger bond, okay? And that is going to give us a higher frequency. And if you notice and you look at Hooke's law, we've got the wave number here. It equals K, which is just a constant, and the square root of the force constant over the mass, okay? And when we talk about that force constant, that's just the strength of the bond, okay? So that force constant is just bond strength. All right? So that's in the numerator, stronger bond, higher frequency. This is in the denominator, and we've got frequency over here, so smaller mass, higher frequency. Directly proportional, inversely proportional. And so this describes the frequencies that we see in the IR. Now, we can break the IR up into 4 predictable regions, okay? And when you have here about 4,000 to 2,500, these are lighter atoms, so they're going to be at a higher frequency. So these are things like carbon, oxygen, and nitrogen, and their bonds to hydrogen. Here, 2,500 to 2,000, we get stronger bonds, which have a higher frequency. Carbon-carbon triple bonds, carbon-nitrogen triple bonds. Then double bonds, which are a little weaker, are between 2,000 and 1,500. And then single bonds, carbon-carbon, carbon-oxygen, carbon-nitrogen, and then carbon and halogen show up down here in the fingerprint region. So we're going to really kind of hang out in the 4,000 to 1,500 range. And so we'll be looking at double bonds, triple bonds, and bonds to hydrogen when we analyze our IR spectra. Now, we can break that down even further into some really important bond types. Now, here are common bond types that we're going to talk about. Here's their approximate wave numbers. And this is approximate because wave numbers are going to be influenced by other functional groups on the molecule. Now we can use not only wave numbers, but intensity to help us identify what functional groups are in a molecule. For example, the OH functional group here overlaps with the NH functional group, so they have approximately the same wave numbers, but there's a really big difference. The OH is very strong and broad. It's going to be a really broad peak, whereas the NH peak is not very broad and it's not very strong. It's going to be a medium peak. And so we'll be able to use some information like that to help us make identifications of those functional groups. Now, one of the things I want you to look at here is the sp3 carbon, the sp2 carbon, and the sp carbon. And notice that these carbons, when they're bonded to hydrogen, have different wave numbers, right? And so even really subtle differences that affect the bond strength can affect the frequency of IR absorption. So remember, the higher percent the S character, the stronger the bond, and then that results in a higher absorption. So you get a higher wave number of absorption. So increasing percent S character, increasing wave number. And so that's something that we can see in our IR spectra. Now, another kind of characteristic that you have to watch for is symmetry. For a bond to absorb in the IR, there must be a change in the dipole moment during the vibration. So symmetrical nonpolar molecules, like the one seen here, where there's 100% symmetry, do not absorb in the IR. And so because they do not absorb in the IR, they're said to be IR inactive. And so that's something that's unfortunate about IR, is that you have to have molecules that don't have symmetry. Another kind of interesting thing that we see in the IR is that conjugation of a carbonyl group with a carbon-carbon double bond or benzene is going to shift the absorption to a lower wave number. So conjugation of the carbonyl group with a carbon-carbon double bond or benzene shifts the absorption to a lower wave number by about 30 wave numbers. Now, what am I talking about here by conjugation? Because we haven't talked about conjugation yet. When we talk about conjugation, that's just going to be alternating double, single, double bonds. So we have alternating double, single bonds, right? So double bond, single bond, double bond. This is a conjugated system. What that means is electrons are spread out over this single bond, okay? A conjugated system, another example would be double bond, double bond of benzene, okay? If you have two sigma bonds that separate the double bonds, that is not a conjugated system. So it has to be alternating, separated by one sigma bond. Two sigma bonds, and it's not conjugated. So let's look. If we have this functional group, the ketone, but the ketone is next to a benzene, so it's conjugated, notice that we end up with a lower wave number. Same things happens here between the ketone here and then the ketone and then the alkene. We get a lower wave number because that is a conjugated system. So you can use IR to figure out if you have a conjugated system or not. And so that's very helpful. The other thing that we see is that basicity is going to affect the absorption on IR. And so, for example, the more basic that Z is, and Z is just any molecule that is not carbon, right? So the more basic Z is, right, the more it donates its electron pair, and the more resonance structure three contributes to the hybrid. Okay, so look, we've got this resonance structure, then these electrons can come here and form a double bond, and then we have resonance structure 3 here. So as a result of this, right, as the basicity of Z increases, right, the frequency of the carbonyl absorption decreases. So, for example, we have a double bond here. There's the carbonyl, here's an oxygen, here's a nitrogen. Oxygen is less basic than nitrogen, therefore nitrogen is more basic than oxygen. And so this is more basic, meaning that we're more likely to have this resonance structure contributing to the hybrid. And so we end up with a lower wave number here. So that's something else that we will observe when we look at IR spectra. In the next screencast, we are going to do a bunch of examples of analyzing IR spectra. If you have any questions, please feel free to stop by my office.